In this video, we're looking at solving exponential and logarithmic equations. This particular video focuses on exponential equations where the bases can be written so that they're the same base. So your first step in solving exponential equations is asking yourself well, this power here is, or this base here is a 5. Can I write this so that it is 5 to the power of something? In this particular example, the answer is yes. If you can write the base as the same, then it makes the most sense to do so, because 5 to the power of something equals 5 to the power of something. Well, those somethings must be equal to each other. Otherwise, 5 to the power of something doesn't actually equal to 5 to the power of something. So in this particular case, we're dropping the bases. Yeah, I know, it's a funny joke. But we're going to drop those bases there, and we're going to get 3x minus 6 equals to 3. And then we're going to solve this, and notice that we can get x as what we need it to be in order so that the two exponents are the same, so 5 to the power of blank, being 3, is equal to 5 to the power of 3. So I'm going to add the 6 to both sides. I'm going to divide by 3, so x is going to be equal to simply 3. Again, adding the 6, giving me 9 over here, dividing by 3 gives me a 3. Now, again, we should check these. It is not necessary for exponential functions because they don't have any domain issues. But if the question asks you to check, you should check. You need to check. And if the question doesn't ask you to check, it's safer to check just to make sure you didn't make any silly mistakes throughout the process of this problem. The next example we're going to look at is, again, very similar to that, such that we have 8 to the power of x plus 2 equals 4 to the power of x minus 3. Now, you might ask yourself, well, can I write 8 as 4 to the power of something? And the answer is no, at least not sufficiently and not smoothly. The same goes for 4. However, what we can do is we can rewrite the 8 so that it's 2 to the power of 3, and then that whole thing is still to the power of x plus 2. Equals to, and we can rewrite the 4 so that's 2 to the power of 2, so that whole thing is to the power of x minus 3. Now with this done, we can manipulate the exponents. Power to a power, we multiply those exponents. So it's going to be 2 to the power of 3 times x plus 2 equals 2 to the power of 2 times x minus 3. In which case, with those two exponents being manipulated such that the bases are the same, we can again drop the base and set the exponents simply equal to each other. If I simplify this, I'm going to get 3x plus 6 equals, and if I simplify this, I'm going to get 2x minus 6. And trying to solve this will simply be solving a linear equation. Notice how most examples of types of new functions we manipulate with have a specific process that we use to start, and then in the end it either breaks down to either a linear, a quadratic, or a basic polynomial. So in this case, I'm going to go ahead and I'll subtract the 2x from both sides because I like my x's to be positive, which means I'm going to go ahead and subtract the 6 from both sides, giving me negative 12 on this side, giving me a positive x on this side, and therefore x should be equal to a negative 12. Again, if we go ahead and plug this in and check, it should come out to be the same. It's 8 to the power of 10. And it's 4 to the power of a negative number, or sorry, negative 10. And again, those two numbers should eventually equal to each other with the appropriate amount of simplification. That's the first method in solving logarithmic equations. However, there are more ways to solve exponential equations. Speaking of, say, this one to start, if I have 5 to the power of x equals 134. Now, again, this is a specialty case of a more probably generic case. While these two cases up here are smooth, simple, and are easy to identify, this one, well, you'll notice that if we ask ourselves, can I write 134 as 5 to the power of something? If I could, then this problem would be really easy. But 134 is not some multiple of 5, so there's no nice way to manipulate that. So in this case, what we're going to do is we're going to make sure that this exponential function is isolated. And then we're going to go ahead and use a logarithmic function, and we're going to apply that logarithmic function on both sides. In most cases, that logarithmic function will be the natural log or the common log. I generally choose to use the natural log on both sides of the equation because it's just less letters to write. So it's the natural log on both sides. Now, why would we do this? Well, if I were to do it this way, this x now, because of the properties of logarithmic expressions, this x can drop down in front. That's again using the power rule. So I have x times the natural log of 5 equals natural log of 134. Well, now you'll notice that the x is no longer in the exponent, and it's sitting outside of a log function. And if I divide both sides by the natural log of 5, I will end up with x equals the natural log of 134 divided by the natural log of 5. Now, there are other ways to solve this expression. We don't necessarily have to use the the natural log to deal with this. What we can do instead, however, is if I had 5 to the power of x is equal to 134, I could take the natural log base of 5 on both sides. Now, the only problem with natural log of base 5 on both sides is that I can't utilize that log base in a calculator. So if it asks me to solve, well, then this is going to be the appropriate way to solve. But if it asks me to approximate, then this method isn't going to do well for me to approximate unless I use the change of base formula. You'll notice here log base 5 of 5 to the power of x is nothing more than x. And notice how in one fell swoop I can get this solution. You'll have to notice that these two solutions are the same. If I were to apply the change of base formula to this to get to this, natural log of the inside on top divided by the natural log of the base on the bottom. And sure enough, those two things are the same. So you can do one more step with this particular method and still get to something that you can plug into a calculator and approximate. And in most cases, these types of questions will ask you to solve, find the exact value, and they'll follow up with approximate. So again, you'll have to take this value right here. This is a valid solution for the exact, but you're going to have to manipulate it to get to this so that you can type this into a calculator and approximate. The next example for these are going to be 10 to the power of x equals 8,000. Very similar type of problem. The only difference is again, the fact that if I try to look at the bases and make them the same, I can't make the base of this the same as this. Now sure, I can pull the 8 out, and then it'll be 8 times 10 to the power of 3, but that still doesn't account for the fact that this is 10 to the power of x. I can't make this side be just 10 to the power of something. So I'm going to go ahead and have to apply the same properties to this. But this time I'm going to use log base 10 because the base of 10 is already part of my exponential function. So log base 10 of 10 to the x equals log base 10 of 8,000. Over here I can go ahead and bring the x down, or I can just follow the rules of what power of 10 gives me 10 to the x. It's x equals, and then over here I can simplify in some ways, or I can just leave it as is for the exact value, and then that exact value I can type into a calculator because it is log base 10. If it asked me to simplify this solution, I could see log base 10 of 8 plus log base 10 of 1,000, because I can tear this apart. And then you'll notice that log base 10 of 1,000 right here is nothing more than 3. So I have 3 plus log base 8, or log base 10 of 8. And the reason why I write it this way is so that I don't confuse the 3 being inside this log function over here. I prefer it to be this in this form. The last example we can play with in exponential functions is a really nasty example. It applies to the same concept as just simply taking the natural log of both sides, but we're going to do that in a separate video specifically because it's such a heavy problem. The heavy problem, again, starts out like this, and again, we will use a different video because it takes so long to finish this particular problem. But again, you'll notice that because the two bases on both sides both have variables to them, and they're both different bases that can't be written in the same form, that is going to give us all sorts of nightmares. But we're going to do that in a separate video.